Hi, in this video we're going to look at an introduction to vector fields. So I have some images here that are just some examples of vector fields, just to start with a look at that. So the first image that you see here is a vector field that shows wind vectors on a particular date. So this is a weather map, and so you can see you've got all these different vectors pointing in different directions. Some vectors are longer than others, some are very short. So all kinds of different vectors, different places on this map here showing direction and magnitude of wind speed. The second image over here is one that I just created using CalcPlot 3D, and so I'll show you how to do that as well. It's got a surface on it, but it's also got all these vectors all over the place, and it's really more of a three-dimensional picture of a vector field. The one right below that here is one that I found on a website. It's from MIT, a visual tour of classical electromagnetism. And this is supposed to be a vector field representation of electromagnetic field for one positive charge, that would be the orange one, and one negative charge. And so you can see you have all these different vectors here pointing in different directions and different magnitudes as well. And then the one right below the weather map over here is one also from a sort of physics example. This is from an OpenStax university physics textbook showing a gravitational field near the Earth's surface. So you can see on that one the Earth is represented by that blue dot near the origin on this coordinate system. And all the vectors are pointing toward the Earth, so the gravitational pull toward the Earth. And you notice that the magnitude of the vectors is a lot longer when you're closer to the surface of the Earth, and then a lot shorter when you're farther away from the center of the surface of the Earth. So visually, all these just give you some different examples of vector fields. They have a lot of practical applications. But the basic idea here is that you've just got a lot of different vectors at a lot of different points. And so we're going to scroll up here and look at a definition that's going to be useful for some of what we're going to work with. Vector field is a function that inputs points and outputs vectors. So just to kind of summarize and compare with some of the other kinds of functions we've looked at, you looked at functions in algebra and Calc 1 a lot, things like f of x equals x squared. And those are the kinds of functions that input real numbers and output real numbers. And then another kind of functions that we looked at the beginning of this course were functions like r of t, vector valued functions. Remember that really the inputs here are real numbers, but the outputs of this are vectors in Rn. Okay, and then in the last couple chapters, we have been working with functions like f of x, y, z, maybe equals x, y squared, z cubed, or something like that. And so just to kind of be clear about what those are, those would be functions that input points in Rn and output real numbers. And so if you look at the way I've kind of arranged this, you can see that really essentially we've got sort of one piece that's missing here where we would input something in Rn and we would also output something in Rn, or maybe in Rm, even a different dimension. We're going to talk about vector fields that go from Rn to Rn, generally from R2 to R2 or R3 to R3, but where you would input maybe a point and get out a vector. And so we will talk about some notation associated with those kinds of functions. So just like we have standard ways to denote all of these others, we use f of x to denote the kind of ordinary functions you dealt with in Calc 1, r of t, when you see that kind of notation, you know what we're talking about, f of x, y, z with a lowercase f, you know what we're talking about there. We have some kind of standard notation that we use for vector valued functions as well. And so I'm just going to scroll up here and talk about that. So vector valued functions, if we're inputting a point in R3 and getting out a vector in R3, we might write f, and if you see that type, that'll be bolded. Often we'll use a capital F, although sometimes we'll use lowercase letters, especially if the vector field represents some specific thing like velocities or something like that. But generally in our textbook we use a capital F, and that'll be bolded, or maybe it'll have a vector barb over it to indicate a vector of a point. So we're inputting a point, x, y, z, And what we're going to get out is a vector. So we need vector notation on our output. So I can use the brackets and commas or the IJK notation. But just like for the R of t, we've got little functions in each component. And our textbook, and this is pretty common in other books as well, likes to use m for the function that gives the I component of the vector, and n for the j component function. And then O probably is not a good idea because it looks like 0, so P for the k component function. So we might write capital F bolded or with a vector barb over it. So we could write it like that, or we might also write that in bracket notation. I'm going to leave off the of XYZ, so M, N, P. If I have one in 2 dimensions, you'll see here my example that I have typed here is just a vector function that inputs a point in 2 dimensions and outputs a vector in 2 dimensions. So in that case, you might write f of xy equals m of xy is the I component function plus n of xy be the j component function, or with brackets and commas as I have typed down here. Okay, so one of the first things we think about anytime we talk about any kind of functions is inputs and outputs and how we might think about graphing those. So let's look a little bit at this example and we'll graph that. So for this one, I'm going to do a little bit of the graph by hand, and then we'll look at how we might use a computer to draw a graph of this. So the inputs are points, so I'm going to write x, y for my points, and then my outputs are vectors. And so I'm just going to make a little table here with some input-output pairs and draw them. And then we'll look at a computer graph that'll help us think about the graph maybe a little more fully. Okay, so we're going to just plot lots of points. So for example, 0, 0, 1, 1. So when I plug in 0, 0, I'm just putting in the 0 for x and the other 0 for y. So I'll get 0, 0 plus 0, or that's just the 0 vector. So at the origin, I really just have the 0 vector, so I would just represent that as a point. At 1, 1, I would get 1, 2. And that vector is associated with a specific point. So I want to go over here to the point 1, 1, and from the point 1, 1, I would go over 1 unit and up 2 units. 1 unit in the horizontal direction and 2 units in the vertical direction. And so there's my vector f of 1, 1. And so I draw that with its tail at 1, 1 because this vector is associated with the point 1, 1. So I put its tail at the point 1, 1. All right, I'm just going to pick a couple of other points here. So at the point 2, 0, I would go right 2 and up 2. You can maybe see that if I tried to plot some other vectors that they might actually end up going over each other, across each other. And we'll see that when we look at some computer images and talk about some ways to handle that when we do that. Also for all of these points I've plotted have positive or 0, x and y inputs, and so I just want to do one in another quadrant. I'll just do the point negative 1, 1. So a lot of times students have a hard time interpreting the difference between the point 1, 1 and the vector with different components. So it's handy to actually plot a few by hand so that you get the idea of the separation between the points and the vectors here, that they're not really the same thing. So when I'm at the point negative 1, 1, so there's my point, I'm going to draw the vector that goes 1 unit left and 0 units up. So that vector is going to be pointing just straight left. Okay, we're going to look at graphing this on the computer here. Okay, so what I've pulled up here is CalcPlot 3D. So we've used this a lot to graph all kinds of things. And I'm going to go over here to this menu that says Add to Graph. And when I click on that, you see that one of the choices here is vector field. So I'm going to choose that. I do want to probably get rid of the graph that I already have on there. So actually I'm going to scroll down a little bit here and I'm going to uncheck the box on the graph that I already had graphed. You'll notice when you pull up Add Vector Field that there are some boxes that come up, M, N, and P. So those are those component functions. I'm going to go in this first box and just type what we did for the one we were just drawing, x. And then in the second box, I've got x minus y, which is what we were already graphing. Okay, since I'm going to just graph a two-dimensional vector field, I just put 0 in the k component function. And so there are two things I'm going to do here so that I can see this vector field. One is, since I'm going to be looking at a two-dimensional vector field, I'm going to check the box that says restrict view to 2D. I'm also going to use a constant primary color, and I'm going to go ahead and click the box right next to the M, and I should get to see my vector field. All right, so there is the vector field. You'll notice that, for example, at the point 2, 0, where we plotted a vector, that the vector that's shown in this vector field is much shorter than the one we did. That's because there's this box that says scale vectors by dividing by, and there's a number 4 in that box. So I'm going to change that to 1 so that it does not scale the vectors, and we'll look at that. Okay, so this is the vector field that we were drawing. So you can see at the point 2, 0, I've got a vector that's over 2 and up 2. But one of the problems with a graph like this is that all these vectors tend to be all on top of each other. And so when you look at all these vectors, it's kind of hard to see what's going on. So it's really common that when you look at vectors that represent things like the electromagnetic picture that we looked at, and also the wind speed vectors, that those are scaled so that they're not all on top of each other. So I'm going to go back and change this to 4. Notice also that I chose some nice whole numbers to plug in when I was plotting vectors by hand, but you can see here on the computer screen that they've plotted some vectors at some fraction points x and y. The domain of the function really is all of R2 of that function we were looking at, so you could plug in points anywhere, but what you're looking at here are just a few representative vectors. If you plotted vectors at every single point, they would all be on top of each other and you wouldn't be able to see anything. So the number of vectors here along the x-axis and y-axis, you can control that so it can plot more or less vectors. So I'm going to change that and make more. So here's the vector field where I now have 15 vectors across and up and down. So it just gives you a little bit better picture of what's happening in the vector field. You can also change your window. This is just the default setting. My x and y axes going from -2 to 2. So that controls what points it plugs into the vector field. I can change that in the same way we always change that, using the window settings up above. And you can format your axes and make those bigger so you can look at a bigger picture if you want, or smaller. So although we're going to be able to look at a lot of vector fields that are generated by a computer, it is helpful to sometimes be able to interpret some very simple kinds of vector field equations without having to graph them, so that you have a sense of what these look like. So I've just written down a couple of them here. If you have a vector field equation where the first component is 0, if you just think about what that would look like, that means that every vector in the vector field has a horizontal component that's 0, and then the vertical component could be positive or it could be negative. So all of the vectors everywhere in this vector field would all be vertical. They might be pointing up or they might be pointing down depending on the sign of that n function, but all of the vectors in that vector field would be vertical because they all have a horizontal component of 0. Similarly, for this next one, if you have 0 in the j component, then all of the vectors in your vector field will be pointing to the right, or maybe to the left, or maybe to the right in some parts of the graph and the left in other parts of the graph, but they all have a vertical component of 0. So all of these vectors are horizontal vectors. If you have a vector field where your component functions are the same, so for example, if I had a vector field equation that was, say, x squared comma x squared, or x plus y comma x plus y, where my m and n functions were the same, one of the things that would be important to understand about that vector field is that however far you go horizontal, you're going to be going the same amount vertical for every vector in that vector field. So the vectors are always going to be along the lines y equals x, or vertical shifts of those. So they're always going to have these 45-degree angles, form 45-degree angles with the coordinate axes. And they might be pointing in different directions in different parts of the vector field, but that's kind of a handy thing to know as well. If you have vector field equations where you can tell that the first component or the second component is always one sign, that can be helpful in thinking about what that vector field looks like. So I just have an example here. If I know I have a vector field equation where, say, the horizontal component is always positive, that means all of my vectors would be going to the right, and then knowing that the vertical component, the j component of that vector field, is negative, that would mean all my vectors are going to the right and down. So everywhere on this vector field, maybe at different angles of to the right and down, but I would have vectors that are going to the right and down. And so that's handy to know, to be able to think about the sign of your component functions, to visualize what that vector field would look like without necessarily having to get a computer to graph that. All right, there are a few problems on your assignment that ask you to plug in some points and draw some vectors. You can use a computer to help you with some of that, but it's handy if you do a little bit by hand just to get a sense of what's going on.